Today's lesson is about standard scores and percentiles, which I'm sure many of you have heard of because you've taken the ACT or different tests that have talked about percentile scores. But that's what we're going to look at today is standard scores and percentile scores. You are going to need your calculator, so make sure that you've got that for this lesson. Okay, first of all, and this is not on your notes, but I just want to talk about why we even need standard scores. So here's a situation where you would need a standard score. We looked at this yesterday. Yesterday we talked about Dutch men being exceptionally tall people in the world and how their average height is 184 centimeters. They have a standard deviation of 8 centimeters. So if I asked you this question, what percent of Dutch men are taller than 187 centimeters? Here's the problem. I have a mean of 184. My standard deviation is 8, and so 107 or 187 centimeters does not fall on a whole number standard deviation line. It is not exactly 1, 2, or 3 standard deviations above or below the mean. And so when that happens, we need to have another way to measure percentiles or measure scores or to be able to compare data or make a guess with it. Okay? So when data points don't fall on a whole number deviation mark, you have to find standard scores instead. Here's another situation. I have two people, one that took the SAT and one that took the ACT. Jenny scored 600, which is certainly better than average on her test. Gerald scored 21, which is again better than average on his test. Okay, and I have to award a scholarship, and I'm going to give the scholarship to the person that did the best, and I want to know who should I give it to. Well, I don't know. They took different tests. So the question is, who did better on their test? Did Jenny do better compared to the people that she took the test with? Or did Gerald do better compared to the people that he took the test with? And I'm talking about two different tests here, so I'm not being able to compare apples to apples. And when you can't compare apples to apples, then what you need to do is you standardize, that's what it's called, standardize their scores. You get standard scores so that you can look at standard scores and percentile scores and then be able to make a comparison between the two. And then you do have a way to compare them, okay? But not until you standardize their scores. So first of all, a little bit about what a standard score is. A standard score is a number that just gives you how many standard deviations a piece of data is, either above or below the mean. If it's above the mean, it'll be positive. If it's below the mean, it'll be negative. Okay? The little formula is here for how to calculate a standard score. You're going to take the observation or the raw score. It might be just kind of whatever you're talking about in any given situation. If it's the height or a score on a test or a weight of sugar or something, okay? But the raw score minus the mean and divide that by the standard deviation. Standard score is also called a z-score. I'm not sure why they use the letter z, but they do. And there you go. Okay, we looked at this normal curve yesterday that certainly labels standard deviations above or below the mean. You know that. But you also need to know that things don't always fall perfectly on exactly 1, 2, or 3 standard deviations above or below the mean. So if I said to you someone scored 1.2 standard deviations above the mean, that means they'd fall like right about here. If I said to you someone scored 2.3 standard deviations below the mean, they'd be right about there. Okay? So just so you know that. All right, we are going to take our first example and kind of look at it here. This has a survey of daily travel times, how long it took people to get to work, and I just sort of abbreviated that, but how long it took people to get to work on several different days, okay? So if you calculate this data into your calculator, which you can put this into your calculator. You can put it in list 1. You can find the mean, again, by going stat over to calculate, one variable statistics. The mean is the x with a line above it, and the SX is the standard deviation. Okay? So it'll give you that data, or give you that information if you put this data into your calculator. All right, I am asking you to find standard scores for these 3 drive times. Okay, the first one would be 26 minutes. And so to find the standard score for 26 minutes, again, to find the z-score, you take the raw score, which is 26 minutes, minus the mean, which was 38.8 minutes, divide by the standard deviation, which is 11.4 minutes, and you get negative 1.12. Typically, standard scores are rounded to 2 decimal places, just so you know that. And what that means is that the person that drove 26 minutes was 1.12 standard deviations below the mean. Okay? You'll do the same thing with 33 minutes. So the observation or the raw score minus the mean, divide by the standard deviation, and this time you'll get negative 0.51. So this person scored just a little bit above, their drive time was just a little bit below, sorry, not above, below the mean, a half a standard deviation or so below the mean. Okay, and then 65 minutes, same thing. And this time you should get 2.3 for a standard score, which means they scored 2.3 standard deviations above the mean. Okay. Just so you know, if you scroll down here, this is kind of a graph of where these are plotted. The 26 minutes is 1.12 standard deviations below the mean. The 33 minutes is 0.51 standard deviations below the mean, and the 65 is 2.3 standard deviations above the mean. Okay. So the next question would be this. How many minutes would the travel time be if the standard score was 1.4? So the standard score, again, tells you how many standard deviations above or below the mean you are. And so you're going to get a z-score, again, and here's your little formula. The observation minus the mean, divide by the standard deviation. Well, in this case, this 1.4 is the z-score. I already know the z-score. What I don't know in this case is the observation, or the raw score. So I'm going to make a handy-dandy little equation. I'm going to call that observation x. And, oops, I can plug a number in for mean, sorry. The mean is still 38.8 in this situation, and the standard deviation is still 11.4. And then, you know, to solve this equation, you're going to multiply both sides by 11.4. and add 38.8, and when you do this, your x will come out to be about 31.92 minutes. Okay, so if you're 1.4 standard deviations above the mean, your travel time should be about 31.92 minutes, and that hopefully will make a little sense. You know what? I just messed up back there, you guys. Sorry. You know what I did? I didn't do this right. 1.4 times 11.4, and then add the 38.8 to it. Should not be that number. It should be instead 54.76. So sorry about that. Minutes. Okay? And that makes more sense. 1.4 standard deviations should be about 54.76 minutes. Okay? All right, then what we want to look at, you guys, is we want to look at some percentile scores. And percentile gives you a way to compare any piece of data to any other data in the set. It ranks the scores and tells you how many pieces of data, or how many observations, or how many scores lie below the given percent. Okay? You are going to use this to find percentiles on your calculator. It is a normal CDF function. You do it, and I'll just show this to you because I will do this with you, but you do it with normal CDF on your calculator, which is second variables, and then you're going to go to the normal CDF function, and you're going to use the left edge standard score, the right edge standard score, and if you don't know the left edge, you're going to use negative 1,000. If you don't know the right edge, you're going to use positive 1,000, and I'll talk a little bit why I want you to do that when it comes up. But for now, I need to open my TI graphs so that I can do this with you. Okay, so percentile scores we're going to use our calculators for. There is a table for finding percentile scores, but I am not going to have you use the table. I'm going to have you use your calculator because it's much more accurate. Okay, so on to this. All right, so same situation. We're still talking about drive times, and I want to know what percentile is 33 minutes drive time. What percentile does that fall at? And so I'm going to look at this, and the thing is this. To do normal CDF, I cannot stress this enough, you have got to have z-scores first. If you don't have z-scores, you're going to have to calculate them. Okay, so I'm going to do this. We already know the z-score for 33, but again, if I didn't, I would go 33 minus the mean, divide by the standard deviation, and we already know this, we would get negative 0.51, which is negative 0.51 standard deviations below the mean, okay? Below the mean. Okay, so my question is this. What percentile is 33 minutes drive time at? Again, percentile is always going to ask you how much data falls below that point, to the left of that point if you were to graph it. So in this situation, I want to know what percent of the data falls in here, okay? Now, I know that 33 has a standard score right here of negative 0.51. Okay. The problem is I don't have a number for this left edge, and if I don't have a number for the left edge, then I'm going to call it negative 1,000, and that just means that it's 1,000 standard deviations below the mean. And you want your calculator to have just a crazy number in there so that you make sure you get every data that could fall into that tail. Okay. So that's what you're going to use. If you don't know the left edge, you would use negative 1,000. If you don't know the right edge, you would use positive 1,000. But here we go. Then you're going to go to your calculator. And again, if you were doing this on a quiz or a test, what I would want you to write is I would want you to write what you put into your calculator for me. So on this case, I would want you to say, I went to the normal CDF function, I put in a left edge of negative 1,000, and I put a right edge in of negative 0.51. And then at that point, you can just give me an answer. So this is the work that I expect you to show, is this piece right here. Okay? Then you're going to put that into your calculator, and you are going to do this. Okay, so you're going to go second variables, which is also distribution. So second variables. You're going to go to normal CDF, which is number 2. The left edge in this case is negative 1,000. Then you need to put a comma in. The comma is right above the number 7. And then the right edge in this case was negative 0.51. Close the parentheses, hit enter. And you get this. Notice it'll spit it out as a decimal for you, which you then need to convert to a percent. So this is 0.0350, which is really 30.5%. Okay, so in this case, I get 30.5%. And the question is, what does that mean? So what that means is this. It means that 30.5% of the time, drive time will be less than, I'm sort of running out of hardware or realty space here on my smartboard. 30.5% of the time, your drive time will be less than 33 minutes. 30.5% of the drive times are less than 33 minutes. That's what that means. Okay? Then the next question, what percent of the time will the drive time be longer than 65? Longer than 65. So I'm going to go up here. I'm going to erase this so that I'm not messing with this here. Longer than 65 minutes. Again, I already have calculated a z-score for 65 minutes. I don't need to recalculate that. I showed you in Part C how to do that if you needed to. But longer than 65 minutes would be how much is in this tail. Again, I know the z-score. You have to know the z-score, not the raw score. You have to put in z-score. So you're going to go to normal CDF again. Okay. You're going to put in the left edge of the area that you're trying to find. Again, the left edge is z-score, not raw score. So the z-score right here would be 2.3. The right edge over here, I don't know, and so I'm going to use positive 1,000 for the right edge. Okay. So I go over here. You need to tell me that you're going to do normal CDF. The left edge z-score was 2.3. The right edge z-score, I'm going to use 1,000. And my calculator spits out 1.07%. Okay. And again, that means that 1.07% of all drive times are going to be longer than 65 minutes. Okay. Then the last part, what percent of the drive time will be between 26 and 33 minutes? So this time I'm going to go up here. Again, I'm going to erase this so that I'm not messing anybody up. Between 26 and 33 minutes. So that means I want to find the area under this normal model that fits anywhere in between here, between 26 and 33 minutes. Again, you must use z-score. You're not going to do normal CDF and use 26 and 33, but you're going to use their standard scores. So if you didn't have their standard scores, you would have to calculate them first. Okay, and again, you do that by doing raw score minus the mean divided by the standard deviation. So here I'm going to go again, normal CDF, and this is the work I would expect you to show is just what you put in your calculator. The left edge z-score in this case was negative 1.12, and the right edge was negative 0.51, and I get 17.37%. And you can check that out for yourself. Okay, normal CDF, negative 1.12, comma, negative 0.51. Okay, so what that means is 17.37% of all the drive times fall between 26 and 33 minutes. Ooh, look at that. I already have them on a separate screen. Okay, here we go. Example 2. Your company packages sugar, and they sell it in 1 kilogram, which is the same as 1,000 grams, bags. So you decide to check their accuracy and weigh a sample of bags. When you do, you see that the mean weight is 1,010 kilograms. So on average, these bags are heavier than they need to be. They have a standard deviation of 20 kilograms. Okay, so here's what I want you to know what I did. This follows a normal model. I should have told you that, but you can assume normal in this case, which I should have told you in the situation, but I didn't. So the mean is 1,010. Standard deviation of 20 means it's going to go up 20 every time on a standard deviation line, or down 20 to go above or below. Okay, and the mean is 1,000 grams, so you can kind of see a picture of what's happening here. Okay. Many bags weigh under the advertised weight of 1,000 grams. And if you were working for that company, you would be cheating your customers if you were selling a whole bunch of bags that weighed less than 1,000 grams or less than 1 kilogram. Customers would not be happy with that, and you might have a lawsuit on your hands. Okay? So you want to make sure that at least almost all of your bags weigh 1,000 grams. Here you have a pretty good chunk of them that clearly don't weigh 1,000 grams. Okay? And you want to figure out what are the chances that if you pick a bag at random, they don't weigh 1,000 grams. So again, what you want to do is you want to figure out what percent of the data falls between here and here, basically. Okay, now this 1,000 grams in this case is a raw score. It's not a z-score. I know that when I want to find percentiles, I'm going to use normal CDF to find percentiles. That's what's going to give me percentiles. So I'm going to use normal CDF to get a percentile. And to do that, I need to put a left edge in, and I need to put a right edge in. Okay, the left edge I don't know, and I'm never going to know it because it goes on to infinity, but you're going to put a really small number in there, like negative 1,000. I need a number for this right edge right here, and it has to be a z-score number, not a raw score, and I don't know the z-score right now, so I'm going to calculate the z-score for that 1,000 grams by doing the raw score minus the mean divided by the standard deviation. And when I do that, I am going to get negative 0.5. Okay, so this z-score right here is negative 0.5. I will put that into my calculator, and again, I will do normal CDF, which is second variables. I'll just do this one really quick with you just to make sure we're good. I'm going to clear this out. Second variables, number 2. The left edge is going to be negative 1,000, comma, which is right above the number 7. The right edge would be negative 0.5. And what my calculator spits out is 0.3085 about. Again, round to 2 decimal places. It'll spit it out as a decimal, but your answer should be as a percent. So you should get 30.85% of the bags. Okay? So that's a lot of bags that are weighing less than 1,000 grams, and that's sort of cheating your customers. Okay, so moving on. Same situation. Now the company wants a much smaller percentage of their bags to weigh below 1,000 grams. Okay? In fact, they've decided they want only 0.6% of their bags to be below 1,000 grams. And that 0.6% happens to fall at about 2.5 standard deviations below the mean. Okay, so 6% or 0.6% equates to 2.5 standard deviations below the mean. So what they want to do is they want to solve the problem by putting a little bit more sugar in each thing. They want to change this. Okay, so what they want to do is they want that 1,000 grams to fall at 2.5 standard deviations below the mean. They still want the bags to weigh 1,000 grams, but now what they want to do is they want to change where this mean value is. They want to change the mean. They want to change how much sugar on average goes into each bag. Okay? So what they're going to do then is they are going to use this formula right here. Z-score equals raw minus the mean, divide by the standard deviation. And they know this. 0.6% of the bags would be the same as negative 2.5 standard deviations. That's your z-score. They want 1,000 grams to be in each bag of sugar. They don't know what the mean is going to be. They're going to keep the standard deviation of 20. That machine is only accurate enough to get within 20 grams of accuracy for each bag of sugar that they do. Okay, so the standard deviation on average is about 20 grams. That machine's always going to be a little above or a little below. But on average, that's what we would need to figure out is on average, how much sugar do we need to put in so that when that machine is off by 20 grams, it'll still give me 0.6% of the bags that weigh less than 1,000 grams. Okay, so that's the situation in this case. So you're going to solve this problem, and I assume you can do the algebra. You're going to multiply by 20 and subtract 1,000 and switch the sign on it, and x should come out to be about 1,050. So what that means is if they put 1,050 grams of sugar on average, keep the machine's accuracy at 20 standard deviation, or a standard deviation of 20 grams, then that's how much sugar they have to put in so that 0.6% of the bags weigh less than 1,000 grams and they're hardly ever cheating a customer. Okay? Now, the problem with that is you're putting a lot of sugar in. You're giving a lot of people a lot of extra sugar, and of course when you're giving them extra sugar, then that is costing you money and product and all that good stuff. So another way to solve the problem would be to do it a little differently and to leave the mean the same as it was originally, which is 1,010 grams, and try to fix the machine so that it's a little bit more accurate. And if the machine is a little bit more accurate, the smaller the standard deviation it will have. Okay? So now what it wants you to do is it wants you to figure out how accurate does the machine have to be in order to keep it so that 0.6% or 2.5 standard deviations are still less than 1,000 grams. So the magic number is still 1,000 grams because that's what I'm selling it for. I want the mean to be the same as it was originally. So now instead of putting more sugar in a bag to fix the problem, I'm going to try to make the machine a little bit more accurate so that it gives me a better prediction of how much sugar will be in the bag. Okay, so again, 2.5 standard deviations below the mean. I want 1,000 grams to be in the bag of sugar. My mean is about 1,010. How accurate do I have to have the machine at, or what standard deviation does the machine have to be set at? So to solve this one, I would multiply by x. Okay, and so then I'm going to get negative 10 equals negative 2.5x, and then divide by 2.5 and solve. And when you do that, you will get 4. Okay, so a standard deviation of 4 grams. So if I can get the machine accurate enough so that it only is off by about 4 grams on average, then I can know that still a very small percentage of my bags will be less than 1,000 grams, and I won't be cheating my customers. Okay. So normal CDF is a key function that you need to know on your calculator. It does convert standard scores to percentile scores, which is really, really important. Tomorrow, the next lesson, we will look a little bit more about another calculator function and be able to go kind of backwards the other way, but I think this is enough information for you to digest in one lesson. So we'll see you next time.